So hey guys, welcome to my channel. I am Suresh Sahu, studying in BTech second year, Bhaskara section of SVC College of Engineering. Today I am here to tell you about the research paper of the data structure and algorithm of sparse matrix. So let's look into the PPT. An Introduction to the Sparse Matrix. This book explores the theoretical and the algorithm aspect of solving large-scale linear system of equation, focusing on direct methods and the algebraic preconditioners. It delves into the challenges of handling sparse matrix, where many entries are zero, and the need of efficient algorithms to exploit the sparsity of the computation efficiency. Now let's come to the motivation part. So first step is the solving linear systems. The core problem addressed is solving linear system of the equation Ax is equals to B, where A is a spare matrix and B is the given vector and X is the unknown solution vector. And now coming to the second part, that is practical application. These systems arise in diverse fields like quantum chemistry, computer graphics, comp- computational, fluid dynamic, power network, machine learning, and the optimization. Exploiting sparsity. The sparsity of A must be exploited to avoid operations with zero entries, leading to more efficient algorithms for solving large systems. Algorithm categories. Two main categories of the algorithm are used, that is the direct method and the iterative method. Now let's look into the direct method. In that we have transforming A, that is the direct method transforming A into the product of the simplest pair matrix, making solving linear system with these factor matrix easier and the less expensive. Now coming to the factorization type, example include close key factorization for the symmetric matrix, LDLT factorization for the symmetric indefinite matrix, and the LU factorization of the non-symmetric matrix. Fill in the reduction. So permitting rows and columns of A can reduce fill in its factors, improving efficiency in terms of storage and the operations. Now let's look into the iterative method. Here we have four steps again. The first would include sequence of approximation. Iterative methods compute a sequence of approximation that coverage to the solution X of the linear system matrix vector product. They use the matrix A indirectly through matrix vector product, making them suitable very for very large problems where A is not the explicitly available. Preconditioning is often needed to speed up the coverage by transforming the system into an equivalent one of the better numerical properties. Now coming to the last one, that is the last part of the iterative methods, that is the algebraic preconditioners. Algebraic preconditioners based on the incomplete factorization of A aim to discard some factors entries to obtain a spaces, but approximately factors for preconditioning. Now coming to the introduction of the terminology and the concept. So let's look into this non-singular matrix. The definition would go like a matrix with a non-unique solution for the linear system, that is Ax is equals to B. Looking into the spare matrix, a matrix with many zero entries. And seeing about the orders of a matrix, the number of rows or the columns in a sequence in a square matrix. Diagonal matrix is a matrix where all often diagonal entries are zero, and a triangular matrix, a matrix where all entries above or below the diagonal are zero. Now coming to the phases of the spare direct solver, here we have the three phase. First one is the symbolic phase, second is the numerical phase, numerical factorization phase, and the third is the solve phase. So let's look into the symbolic phase, where it determines the sparsity pattern of the factor of A without computing numerical values, using only the sparsity pattern pattern S for bracket A. And the second one, numerical factorization phase, computes the numerical values of the factors based on sparsity pattern determined in the symbolic phase. Third one, the solve phase, uses the factors to solve the solution vector X given the right hand side vector b. Now let's look into the comments on the computational environment. Von Neumann architecture. The fundamental architecture of the most computers involving a central processing unit memory that is nothing but the CPU and the input-output mechanism. Multiple functional units, that is the processor with multiple functional units that can perform identical numerical operations in the parallel. Now the data pipelining. Efficient processing of the vector matrix by overlapping operations often supported by the hardware and the software tools. And now looking into the superscalar processes, these processes that enable the overlapping of the arithmetic operation during a runtime, and it is a standard feature since the 1990s. So the spare matrix and their representation in the computer is of four. So first comes the coordinate format and the SCSR and the CSC, and at the end the linked list. So let's go with the coordinate format. That is, it stores individual entries as triple as shown, where I is the row index and j is the column index and aij is the value. And looking into the CSR, that is nothing but compressed sparse row format, stores the column inside by rows values in corresponding array and the row pointers to indicate the start of each row. Now the CSC, that is nothing but the compressed spare column format. So here it is similar to CSR but stores entries by column instead of rows. Now it is linked list. It is a dynamic data structure where entries are linked together, allowing for easy condition and removal of the entries. Hope so you all like the PPT. So just give me a comment